All right. How's everybody doing? Good. Homework's due in my quant class. Office doors like a revolving door right now.
Oh, I think they're muted. I don't think they can hear.
You guys hear us from Brownsville?
It's got the meeting sign.
There you go.
Yeah.
All right, can you guys hear me now?
Yes.
Okay. All right, so give me just a second here to set up. I wanted to try to remember where we were.
We were doing stuff for the one particle state, I think.
Today's the 19th, right?
Mm-hmm. Yeah.
So yeah, so last time we worked through the quantization, right, of the directory. And so we, oh yeah, okay. So we had written down the Hamiltonian, right? We tried to follow the same recipe that we did for the Klein-Gordon case. And so we wrote down the Hamiltonian and plugged in. Okay, so we derived the Hamiltonian, right? And we saw that it had the last time. We had derived the Hamiltonian following the recipe that we followed for the Klein-Gordon case. Right, so we assumed that we have two sets of annihilation and creation operators, right, which we saw we needed a couple weeks ago. And when we derived the Hamiltonian, we found that we had this minus sign here, right, in between these relative signs between the states. Right? And this is with, we assume that these guys obeyed some commutation relation. It's not equal to 0. So I can't remember exactly. But it's not equal to 0, right? So this is what we got. And we said, okay, we're screwed, but maybe, could we somehow go back to our definitions of the fields and exchange what we call B and B dagger, right? And in this case, we couldn't because it'll screw up the commutation relation. So instead, what we did was assume that the anti-commutator of these guys, of the B's, was not 0, right? They obeyed some anti-commutation relation. And then we got the same result. We got the same result, but in this case we could flip them, right? Because we go back to our definition of the field and flip them, because it's not going to screw up the anti-commutation relation. And so what it allowed us to do was define these new operators. We went from B to B twiddle, I think, and what we call B twiddle, or maybe I just went straight to just flipping them. But in any case, we got a Hamiltonian that is well behaved. In other words, we're not going to, from this Hamiltonian, we can't create more and more negative energy particles, right, and drive our total energy negative. And so we think we found a good Hamiltonian. And then the last part, we kind of sketched out the computation of the Feynman propagator for a Dirac field. And it looks similar to the Klein-Gordon case, but it has this weird factor of p slash plus m in the numerator. Plus m. Minus that. All right, so it looks almost identical except for this funky looking p slash plus m, right? And that's what's going to complicate our lives when we go to compute scattering amplitudes. Okay, so everything we've done so far basically fell out of. We started by imposing Lorentz symmetry, right? Taking our Lagrangian-Lorentz invariant. And we all know that Lorentz transformations are continuous transformations. And so what I wanted to do today is start to talk about another type of symmetry, which are discrete symmetries. So discrete symmetries of the Dirac. So that's going to be the topic for today. Okay. And there are actually there are a handful. Well, not a handful, but three. I guess it gives one. Oh,
Maybe zoom out a little bit.
zoom out.
Maybe.
But it's going to get the whole page.
Yeah.
Okay. All right. So there are a few that are important, and well, let me talk about those, and then I'll talk again about how discrete symmetries are used in modern or in model building for models beyond the scale model and stuff like that. Okay, so we're talking about the Dirac-Lagrangian. You know it's Lorentz invariant. There's actually two other space-time symmetries, and these are discrete symmetries. One is parity, which you're probably familiar with, and we'll denote that operator as big P. And this guy takes, it sends, say, our 4-vector Tx, and it flips the spatial component. So it goes to T minus x. Right? In other words, it reverses the handedness of space. Okay? And we'll see that in a little more detail. But there's also time reversal. We'll denote that by big T, and that sends Tx, a space-time point, to minus Tx. So it's like running the movie backwards, right? If you had a movie of some event. Okay? And it turns out that neither of these symmetries, when we talk about transformations, we always talk about continuously, these transformations being continuously connected to the identity operator, right? That's how we build up transformations in quantum mechanics, starting from infinitesimal transformations. It turns out that there's no way to do that with these guys, okay? And so they are truly discrete, okay? Note that both of them preserve Minkowski interval, which is x squared, t squared minus spatial x squared. So they both preserve a Minkowski interval, and like I said, we're going to look at these two in detail today, or as far as I got for the deluge of quantum students asking me questions about your homework. So we'll talk about parity and time reversal today, and the next time we'll talk about another type of discrete symmetry, which is called charge conjugation. And this, as the name implies, exchanges particle with antiparticle. And we'll see how that is implemented in field theory next time. And so, these are theoretically they could be symmetries of the Lagrangian, but you want to ask yourself, are they, do we actually observe, these symmetries in nature? And it turns out that some of them are preserved and some are not. Gravity, electromagnetism, which I'll just write ENM, and strong interactions, or QCD, those guys preserve individually. They preserve the parity, they preserve charge conjugation, and our time reversal. However, the weak interactions are very strange. Okay? The weak interactions have been shown to violate charge and parity separately. Okay? But it seems like to a very high degree, they conserve the product of C and P and T individually. Okay? Now I say, most of the time, or for the most part, they conserve CP. But there are these things called, well, let's just call them rare processes. And these have to do with things called K mesons. And I think now CP violation has been observed in B mesons as well. Right? So these are composite particles made out of quark and anti-quark. These guys, they actually violate a very small amount of CP symmetry. Right? A lot of times, if you look at a talk or something like that, you'll see CP violation written like that. Okay. So these guys violate CP symmetry, and it's a good thing that they do, because we think that's why there's this asymmetry between matter and antimatter in the universe. Okay. So you think, naively you would expect in the Big Bang you create equal amounts of matter and antimatter, right? But when you look out at the universe now, you don't see very much antimatter. Everything's made of matter. And so one of the ideas behind explaining this asymmetry is that through some violation of CP symmetry, you can get rid of or at least keep some of the matter around. However, okay, so these are the things that are conserved. The product of all three, CPT, seems to be an exact symmetry. Okay, so that guy, the product of those three things, and in all the processes that we've observed, or all the experiments we've done, CPT seems to be an exact symmetry. All right. Okay, so let's talk about parity. How we implement parity. All right, and you should know from your days of classical mechanics or E&M that P, our operator P, should reverse the momentum. I'm writing way too much. But anyway, it'll reverse the momentum of a particle, right? I mean, the momentum is, I'm talking about the 3 vector here, momentum. And it'll do that without flipping the spin. So if we're talking about a particle that has spin, it obviously will take a normal 3 vector and reflect it through the origin, right? But the spin lives in a different space, right? So parity or space inversion has no effect on spin, right? And so if you were to think about it in terms of a mirror, right, you would have something like this, where here's my momentum vector, right? And let's say that the spin is going this way. If I operate with with our parity operator, and I go from this to the mirror image, then it'll flip the direction of momentum, but the spin will still be going the same direction. Okay?
But it's different direction.
No, it's still
First one goes another one goes clockwise.
well, they're supposed to be going the same way. So they're going like this.
First one is clockwise.
Does that help?
He's talking about how if you're going this way, and then going that way, it looks different. Now, when you're looking at it from the same angle, not from different angles, then they're the same.
Yeah, the same frame of reference.
Yeah.
How do we choose axis for spin? Then another question. To measure spin, how do we choose axis?
I think it's just arbitrary. I mean, it's just like in quantum mechanics when you talk about spin up, spin down. How you represent spin up and spin down in terms of spinners, like 1, 0 or 0, 1, it's completely arbitrary. It's just by convention. Right? Does that answer your question?
Yes, but if we have moving particles, so probably the easiest way to define up and down is direction of movement of particles. So if it's angular momentum vector has same direction as direction of movement, then it's spin up, and opposite direction spin down. How else we can define up and down?
Well, through a measurement, through you would like the Stern-Gerlach experiment where you pass a beam of spin 1/2 particles through, right? And you find that they split into 2 separate cases, right? And so one of them you call spin up, one you call spin down. Those where those particles end up after they pass through that Stern-Gerlach experiment has nothing to do with their momentum, right? It's a completely, to think of, say spin up or down in the Z basis, it's not really the physical basis, right? The physical Z basis.
It doesn't literally mean up and down. It was a convention because they used the up and down arrows to represent it.
Yeah. It's just an abstract, kind of way of describing it. But the spin up or down, say in the Z direction, has no correlation with the momentum.
Yeah, remember that the spin of particles is not the same thing as classical angular momentum.
Right.
It's just mathematically similar, basically.
Yeah. Okay. All right. So what we want to do is we want to try to develop a way to implement parity in our formalism, right? And if you remember from quantum mechanics, you typically want to implement any type of transformation using a unitary operator, right? And you basically require unitary operators because you want to preserve probability. Okay? So we want to do the same thing here. Okay, so we'll implement it. And the usual notation when you do a unitary operator is so for parity we might write down something like that. But for parity and time reversal and charge conjugation, it's convention to just write this unitary operator as just P. Okay? Don't ask me why, I don't know, this is just the convention. Okay. So what we want to do is figure out how, when we do a similarity transformation on our field using these operators, how does the field behave, right? And to answer that question, we have to ask first, how do the annihilation and creation operators behave under similarity transformation, okay? So here I'm using the fact that these guys are unitary, right, to write down the similarity transformation. So what we've said is that, just from observation, we see that when we perform a parity transformation, that it flips the momentum, the 3 momentum, but it leaves the spin unchanged. Right? So we would expect this guy to change the sign of its momentum argument, but the spin will remain the same. Okay? So this guy will, before parity transformation, it annihilates a particle with positive p momentum and spin s. And after the parity transformation, it annihilates a particle with minus p with a spin s. Okay? And this is up to some constant, some phase, okay, which I'll call eta sub a. All right? Just because we have the freedom of this phase. And we can also do a transformation on our B operators. Right? And here we get the same thing, we get some phase, and we get B minus P. Okay? And like I said, these guys, eta A, eta B, they're just phases. Okay? However, we can actually determine something about these phases, because we know that if I do one parity transformation, I get the momentum vector flip-flopped, right? The direction change. But if I do another parity transformation, I should get back to where I was, right? So in other words, if I do 2 operations of P, right, this is equivalent to identity operator, right? Identity operator. And so that tells us that, taking into account these expressions for the transformations of these operators, that eta A squared and eta B squared are both equal to plus or minus 1. By convention, we choose a plus. Okay. Okay, so we've got, we now understand, how to write a transformation of our annihilation and creation operators. Right, the creation operator, we just take the Hermitian conjugate of both sides of this. So now let's ask, how do these transformations act on the field itself? Right? So I'm going to start by using, so I'm going to write down our expression for the field. So from last time, let me write it so I can save space. This is what we derived last time. And sum over spent. Trying to save space. E to the minus I x plus VP dagger, S dagger. Plus I. And now what I want to do is I want to do a parity transformation on these guys. Okay, so I'm going to hit from the left and the right with the parity operator. You guys see? So I'm going to do that to the left-hand side, right? And these parity operators, they only affect the annihilation and creation operators. Okay, so they would pass through any of this other stuff, the spinners, and or the either the I or PX terms. Okay? So we have this, right? But we know from our definitions before that these things are just flipping the sign of the momentum vector and adding a phase. Okay? So let me write this as sum over S. Okay, now let me plug in those expressions for these transformations. So this is going to give me A to A minus P. B, this is A to B star because this is B dagger. Okay, so I just used those relationships that we had before for the transformation of annihilation creation operators. All right. So now what I want to do is introduce a little trick, okay? Because we noticed that this integral over the three component of the momentum vector is symmetric, right? So what I can do is replace the four vector, say p mu, which would be, normally it's equal to p naught p, right? But I want to flip the sign of this three momentum, okay? So I'm going to replace this p mu with what I'll call p twiddle mu, where this is p0 and then minus p.
Should there be a plus sign or something between the
Yeah, it's minus sign.
minus?
Coming from
Why you just don't put the mu down?
put the
Down. I think according to conventions, it corresponds to
you mean the Lorentz indices?
Yeah.
Yeah, you're right. Particle physicists are sloppy a lot of times with where they put those. So we're not as strict as GR people.
My thinking is instead of introducing another quantity P0, we just change P mu up to P mu down.
P up.
So P up.
Oh.
Down.
It's you're going to see that it's equivalent, but then I would have to flip what the x, right? I would have to
The first component is the same.
because I have p dot x's right and these exponentials,
Right.
right? And so we know that when parity acts on this thing, it's going to flip the momentum. But yeah, what you're saying is right that I could just inside the dot product, and that's what I'm going to do actually, because we want to preserve this dot product. And so what you have to do is you have to replace your x four vectors with the same thing, right? Because space is going to get inverted as well. Okay. So yeah, so you could do a change of variables, or I prefer the change of variables way, right? Because it's you're talking about a scalar there, so it's not like you're writing explicitly p mu up and x mu down. You know what I mean? It's a matter of taste, but it's same result. Okay. All right. So you have to do that replacement. So that means that anywhere I have, say, p dot x, is going to become p twiddle dot t minus x. Okay. So I'm going to write explicitly this four vector and those exponentials. And then also, this might be where making the replacement makes a little more sense. Because we're going to be we want to write out our spinners, right? Remember our spinners involve the dot product of P with those four vectors that we built out of the Pauli matrices. So under this transformation, things like, so if I say P dot sigma, this is going to become P twiddle dot sigma, right? But I need to preserve that dot product, right? So what it's going to become is you have to flip the three component of these guys. So this is actually going to become R. Okay? And likewise, wherever I have P dot sigma bar, it's going to become P twiddle dot sigma. Okay. Right. So what does that buy us? Well, let's see what the spanners look like. So let me take U of P, right? Remember we wrote this as square root of P dot sigma C P dot sigma bar C. And now let me make this change of variable, so this becomes U P tilde. And what I just wrote down, this becomes P dot sigma bar C. This becomes P dot sigma. But this, this, if you think about it, is really just gamma 0 acting on our original form of the U with gamma 0. So I'm making this replacement, so I'm taking P to P tilde, but like we said, we had to flip the sigma and sigma bar. And if you compare that with this guy, think about what gamma 0 looks like. Remember, gamma 0 is the guy that's off diagonal, right, which flip-flops the top and the bottom, okay? So when we make this replacement, when we go from P to P tilde, we pick up an extra gamma 0, okay? Right? And likewise, I can write down the V spinner, and in this case, with P sigma eta minus P sigma bar, eta. And that becomes P tilde dot sigma bar minus P dot sigma. And again, this is nothing but gamma 0 V of P tilde with a minus sign. All right, because we have to put the minus sign on the part that's sigma bar. Okay? All right. So now let me go back to our expression here that we had for this parity transformation of our field. Plug in these guys after we do the change of variables. So we've got P operating on our field. So now we can enter P tilde. Square root 2e tilde. And now I have sum over S, eta A. And I've got A tilde. That's gamma 0. S tilde. And the E to the minus I P tilde dot, and that's the T, right? It's E to the minus P tilde dot T minus X. Okay. And likewise over here, we've got minus eta B star B tilde. God, I can't wait till we get to final diagrams. Yes, P tilde. P tilde dot. Okay. All right, so that's all we've got making our change of variables. I think I've got all the. Yeah. Okay. But remember, what we want is this guy to implement space inversion, right? So what we want is something that looks like when we operate on this guy, let me separate out the time and spatial dependence. Right? We want something that is going to flip this x to minus x. There might be some, there can be a constant matrix out here, right? but we don't really need to worry about that. All we need to worry about is that we get something that flips the sign, right? And you notice, if you look at this, you stare at it hard enough, you notice that if I take eta b star equal to minus eta a, right? If I replace this guy with minus eta a, then I get something that I can pull out in front. And that thing that I can pull out in front is eta a times this gamma 0. Okay? And what I get when I do that, so I plug in here for eta b star, I plug in minus eta a, so the minus gives me a plus sign here. And so then I would get p psi p, and so I would get eta a, gamma 0, and psi minus x, right, somewhere, psi t and minus x. All right, because the only space dependence is coming in through the exponentials, right? So you see that once I pull out the eta and the gamma 0, I'm left with, our original field, but with the spatial part inverted. Okay? All right. So you're buying that? Okay. So now we know how our field transforms. The other thing we have to worry about is, what about psi bar? Right? How does psi bar transform? Okay. And to see that, let's operate on it from left and right with our parity operator. And then remember what psi bar is. It's psi dagger. So I have p, it's psi dagger times the gamma 0. Gamma 0 I can pull out of here, so I have p psi dagger p times gamma 0. Okay. But this p is unitary, right? So I can write this as p psi p dagger of the whole thing. And this thing we just computed, right? We know that it's right here. It's eta a gamma 0 times psi at minus x. So I have eta a gamma 0 psi t minus x. So dagger, and I get gamma 0. So I get, in this case, oh yes. So when I take the Hermitian conjugate of this, I get eta a star. Gamma 0 just is gamma 0. This becomes psi dagger. So psi dagger, gamma 0, and another gamma 0. This we just take back into, write this as psi bar. So I get eta star, psi bar, t minus x, gamma 0. So the difference is just a change in the phase, right? It's the complex conjugate of the phase when I go from transforming psi to transforming psi bar. Okay, so we know how psi transforms under parity. We know how psi bar transforms under parity. Now we need to start to worry about how our terms in our Lagrangian transform. Okay, so in other words, we have to ask ourselves, this is a new term, I don't think I've thrown it out there yet. How do bilinears transform? Okay? So bilinears are objects that we can build out of a psi bar psi. Right? So we've already seen the scalar and the vector, right? Psi bar and psi. And there's a vector one, psi bar gamma mu psi, right? This is the guy that gives us the kinetic term. Right? And this is related to the mass term. But it turns out that there's 3 other types that you can write down. Only one of them I can remember. So, no, I can remember one. I can remember 2 others. So there's what's called a pseudoscalar, right? Where you have a gamma 5 sandwiched between psi bar and psi. And then there's a pseudo vector where you have gamma 5, so mu psi bar. Okay? So I'm going to work out how these guys transform, right? Because they appear in the bare Lagrangian for the Dirac theory, and I'm going to leave these two for homework. Okay?
Instead of gamma.
Oh yeah, sorry. Yeah. Okay. All right. So I'm going to leave those for. Okay, but let me do the scalar and the vector because those are important. Lost my correction. So let me start here. So let me say, okay, P, do a transformation of psi bar psi. And now I'm going to use the fact that these guys are unitary, and I'm going to insert a 1 in between the psi bar and the psi in the form of P times P. And I have psi P. Now I can just plug in what we have, right? This is the transformation that we just computed, and before that we computed this guy. So what I find is that I get modulus squared of our phase eta A, and what? And then just side bar side. And we've said that this guy is plus or minus 1, but plus or minus 1 squares is 1, so we just get back side bar side. Right, so that's simple as that. That's how the scalar, and obviously the spatial arguments of these guys are going to be explicit. Okay. All right, what about the vector piece? So for the vector piece, transform psi bar and mu psi. Okay. And again, I'm going to insert a 1 in between the psi and the psi bar. And one of the p's I'm going to put with the psi, one I'll put with the psi bar. So I have p, psi bar p, and p psi. Good. And what do I have left? So when I do this, I end up with eta a squared. So let me just do this. So I get eta squared. I get the psi bar with minus x. I get a gamma 0, and I get a gamma mu. And over here I get a gamma 0, and I get the psi minus x. Okay? Now remember, these guys don't necessarily commute, gamma 0 and the gamma mu, right? So it turns out that this transformation is kind of a piecewise transformation. So our gamma mu psi p, and this is going to be either plus psi bar gamma mu psi when, or for when index mu is equal to 0. Otherwise, if mu is ij or k, you're going to pick up a minus sign. Okay? And you might think, oh, this is kind of weird, right? But what you see is that it transforms just like a 4 vector, right? And remember, when you build a Lagrangian, you want it to be a scalar, okay? So what we'll do is, and think about the kinetic term, right? The kinetic term is built by the derivative, right? It was like I, W gamma mu. So this is just the kinetic time, right? So now we know that this guy transforms like a 4 vector, and this guy's going to transform like a 4 vector, right? So you actually need this piecewise transformation when you're building Lagrangian, because you want it to be a scalar, right? And this term, you'll see when we get to QED, we'll take a term exactly like this, and we'll dot it into the 4 potential, right? So for the electromagnetic field, okay? All right, and let's see what else I got. Okay, so let me just start on time reversal. I didn't get very far because of annoying arm students. I would never say that about you guys. All right. Yeah. So let me talk about time reversal. Okay, time reversal. When you study in quantum mechanics, I mean, it's just basically, a carbon copy of which is, the way you implement parity. Right? But it turns out in QFT, it's not so simple. And it turns out that for fermions, so in other words, we want to try to represent T as some unitary operator. And in fact, we're going to as a unitary operator. All right. So a unitary operator, or in matrix representation, represented by a unitary matrix. Okay. And it's time reversal, right? So it's if you run the movie backwards, if I'm walking forwards this way, my momentum vector is pointing this way. But if you run the movie backwards, my momentum vector is pointing that way, right behind you. Okay, so we expect that under time reversal that our annihilation or creation operators again are going to pick up a minus sign. Right, that's what we would expect on the momentum part. And also, again, we would expect from time reversal that our field is transformed like this, where you flip the sign of the time. So this is what we want, right? This is what we basically required of our parity operator, and we worked. We were able to build a unitary operator that actually did this. Okay? However, for time reversal, it's not that simple. Okay? And to see why it's not so simple, let's consider doing a time reversal on a field. Okay? And what you expect is if T is the symmetry of the theory, that means it has to commute with the Hamiltonian. Right? In other words, if I want T to be a symmetry, the commutator between T and the Hamiltonian has to be 0. Okay? So let's assume that's the case and do a transformation or a time reversal on our field. Okay? So let me write down our field, right? And I'm going to write this down in a Heisenberg picture, right? So this is like our operator, right? Remember, the way you make an operator time dependent is by operating on it with 2 time I'm doing this in quantum, I can't remember. Time evolution operator, thank you. Right, so these are the time evolution operators, okay? But now let's take this state, okay, and let's do a similarity transformation. So we're going to head it from both left and right with T. Right? So I had T, psi T x, T. And then I have e to the I h t. And I'm going to put in brackets the psi T x, psi h t. Okay? So far so good. We've just written the operator in the Heisenberg picture. We pulled out the time dependence and operated on it from left and right with the time reversal operator. Okay? But now let's operate let's let this thing operate on the vacuum. So operate on the vacuum. Okay, and what happens? Let's see what happens. So let me take T psi x T. And here I have e to the I h T psi e to the minus I h T. Okay. But what does this give me? What happens when this operator hits the vacuum? The energy of the vacuum is 0, right? So this just gives me 1 for this exponential. And so over here I get e to the I h t, and then this operator hitting the vacuum. And so what you see is that this on the right hand side is basically a sum of negative, because this is a plus sign here, frequency solutions only. All right, so it only contains the positive frequency solutions. Okay? But let's look at the left-hand side. All right, so let me take a look at the left-hand side. So I expect T, like we said, to take psi Tx to psi minus Tx. Okay? And that means that the left-hand side, so this thing right here should be this guy, and so I have psi minus Tx operating on the vacuum. There's my left-hand side. And now let me pull out the time evolution operators. And if I do that, I get e, because this is a minus t now, so the e to the minus iht has to go on this side, psi x, and then e plus iht operating. Right? And again, when this guy hits this, the h is going to give me 0 for the eigenvalue, so the exponential just turns into 1. And so what I get on the left-hand side is the sum of the positive frequency solutions. Right? Because I have the positive frequency solutions over here. Okay? So something's not matching up. Right? On the right-hand side, we've got only negative frequency solution. On the left-hand side, we've only got positive frequency solutions if we want t to do what we want it to do, which is reverse the time. Okay? And so you have to think of a way to get out of this. Right? And one way that you can do it, maybe the only way, sure, is to require that the fact that when t goes through a C number, everybody knows what I mean by a C number, meaning it's not an operator, okay? It's a C number, okay? That when it does that, it changes the C number into its complex conjugate. Okay? So this should be weird for you, right? Because you've never seen anything like this. Right? You got an operator, usually operators just pass right through numbers and don't do anything, right? But in this case, we have to require that this time reversal operator, when it goes through a C number, it takes the complex conjugate of that C number. Okay? Now, how does that help you? Well, it helps because if I take t, right, and I hit it on e to the iht, it's going to flip the sign here, right? Because once it operates on some state, it's going to be some number. So it's It's like replacing e to the IHT with e to the minus IHT. And that will get you out of this conundrum where, you know, on one side you have negative frequency solutions, and on the other side you have positive frequency solutions. Right? So the way out of it is to require that this thing obeys this. Okay? All right, so that's as far as I got before they hammered. So we started at 4, right?
Yeah.
4-ish. Okay. All right. Okay. So I don't feel. For a minute there, I thought we started at 4:30. It's like it's only been 30 minutes. But what I'll do is I'll pick it up next time. Finish off time reversal operator. Talk about complex conjugate operator, and then we'll move into how to compute scattering amplitudes and the Dirac theory. Okay. And like I said, we're going to do it a little different than what you guys did in the summer, which was we built it up through the path integral formalism. But here we're going to do a more canonical way. So we're going to talk about something called Wick's theorem and start to build time-ordered products of operators using canonical quantization. Okay. All right. So, and I'll try to come up with a homework assignment. Like I said, one of the problems is going to be doing the parity transformation on those other bilinears, but I'll come up with some other interesting problems too. Okay. All right. Have a good one. See you guys.
All right.